Okay, so this is the title of the talk. It's not the title of a paper because the paper doesn't exist. Roger asked me to summarize some of the work I've done over the years on stock market prices and bubbles. And so it seemed like a reasonable occasion for me to think about the different pieces of work and what other people have done and try and integrate them. Starting point is, let me start in general, which is that, of course, macroeconomic models are particularly interesting because they have expectations embodied in a dynamic stochastic system. And the issue for quite a long time has been how are expectations formed. And of course, the benchmark since the 1970s has been rational expectations. And of course, as we all know, that has a lot of, assumes a lot of knowledge on the part of agents of different types, and it certainly also imposes or assumes some sort of coordination by the economic agents. And this requires, from my point of view and the point of view of many of us, this assumes just too much rationality in some sense, or too much coordination, or both. So what would be a more realistic model? And my general answer to this is given by the cognitive consistency principle, which is that we want to model agents in our economy as about as smart as we are. We don't want them a lot more stupid, and we don't want them a lot smarter in some sense. And I think of there being two main branches on this. One is to think of the economic agents like economic theorists, and the other is to think of them like econometricians, which is, of course, a major dividing point within economics itself. So we call these the adductive approaches and the adaptive approaches. I've done work in both areas. In this particular, today, I'll mainly focus on adaptive learning, which models agents like econometricians. Both of these approaches give you possible mechanisms for coordination. So if there is rational expectations, this would give a story about how it would come about. And alternatively, it may give us new learning dynamics if it does not actually lead to rational expectations. Okay, so we're going to follow the adaptive learning approach, modeling agents like econometricians. And what that means is they've got to select models. They have to have a specification for their forecasting rules. They've got to update parameters over time and use them to make forecasts. So I'm going to just let me outline what I'm going to do, and then I'll do it. I've actually had an interest in bubbles for a long time. One of my first papers was on the sterling dollar exchange rate in the 1980s, where I basically argued that there was an anomalous sequence of excess returns to holding dollars rather than pounds, and it simply would not have happened by chance, and I outlined the various reasons, and that included rational bubbles and irrational bubbles. So I want to start by just briefly reviewing rational bubbles without learning, then explain why I found rational bubbles not compelling, which is largely to do with the fact that they're not stable under adaptive learning. Then I want to talk about what you can do with asset prices when you've got adaptive learning, starting with some fairly minimal deviations from rational expectations. So I've made a list there, which I'll just move through rather than read to you. Then I want to come back to a model that is close to a rational bubbles model. It's kind of inspired by rational bubbles. They're not rational bubbles, they're near rational bubbles. And that's the line there, learning about risk and return, simple model of bubbles and crashes. And if I have time, I'll talk about something that's another variation of this, which I call new rational exuberance, which is some other work that I've done. Okay, so let's start with rational bubbles, because this was a big deal in the 1980s. There were people writing down rational bubbles model that was kind of in the background on the excess volatility literature that we've heard discussed yesterday. So if you have the usual consumption-Euler equation and risk-neutral preferences, then you get out this, this well-known equation in which prices depend on discounted expected prices plus dividends in the following period. So there's a standard fundamental solution to that, which is the price is the present value of expected future dividends. And there are some interesting things that follow from that. If you think you're in a fundamental solution, a no bubbles solution, the fundamentals price inherits a lot of the time series properties of the dividend. So for example, if dividends have a unit root in them, then the fundamentals price will have a unit root in them. Also, fundamentals price and dividends will be co-integrated, and so that's the sort of thing you can test. But if you just look at that as an expectational difference equation, then you can write down the entire set of stochastic processes that solve it. And one way to write those down is that prices are equal to P bar T plus another term called the bubble term, which is just any stochastic process that agrees with that equation there. So you can see if you turn it around that means that in expectation bubbles explode over time. So these they're called rational bubbles because they solve that expectational difference equation, and but they're explosive. So it seems like you might be able to test empirically for the presence of rational bubbles by determining whether or not PT has an explosive root and whether or not PT and DT are co-integrated. I think that's wrong, and the reason was laid out in a short paper I had in the American Economic Review in 1991, in which I basically invented a class of rational bubbles. So other people had invented something similar, which is collapsing bubbles. You have bubbles that explode and then eventually collapse. So the variation I did was simply to make it a periodically collapsing bubble, so it would increase and then crash down to some small positive value and then start off at another trajectory in a random way that exactly met the condition here. And then it turns out that if you do standard tests for the roots, say test unit root against explosive roots or against roots smaller than one, in finite samples, it actually looked like it's a stationary process, not an explosive process. And if you do the standard co-integration tests, you come to the conclusion that prices and dividends are co-integrated. So I'm not going to go through the details of that, but here's a typical simulation. There's the bubbles. This is the fundamentals path. Here I've added on a bubbles simulation. And the fact that the bubble crashes periodically is enough to induce a kind of pseudo-stationarity. So basically the assumptions for the Dickey-Fuller tests and that sort of thing are not satisfied. Okay, so I was going to think a lot more about that, but then I got obsessed with the adaptive learning issue, and so I want to take you through that next. The rational bubbles were very controversial at the time. There were several different arguments against them. Instability under adaptive learning is the one that finally persuaded me that there was an issue there. So I'm just going to focus on that one. Oh, so let me just give you the quick outline of the adaptive learning approach before I do that. So the spirit of the adaptive learning approach is agents are like econometricians. They've got some sort of forecasting model. At time t, they use those to make forecasts. Here it's the forecast of next period's price, or possibly next period's dividend. We'll focus on next period's price. So that's the E star t, pt plus 1 to indicate, the star to indicate that it may or may not be rational in the usual sense. Okay, then then this expectation together with the exogenous variables, for example, current dividends, determines the market price, PT. So sometimes it's called the temporary equilibrium price. So given expectations, given the exogenous variables, this is the price that emerges from the market. Okay, then at the end of the period, or beginning of the next period, you have another data point, and so our agents as econometricians can update their forecasting rule, for example, using recursive least squares. Then you go on to the next period, and the process continues. Agents observe the exogenous variables, they make forecasts, the new market price is realized, and you just let the system evolve. And one question would be, is there an asymptotic convergence to rational expectations or not? Or to some other stochastic process? So that's the adaptive learning approach. So what happens in this simple model if we ask about, well, which solution is stable under learning, the fundamental solution or the bubble solution? Let's keep things as simple as possible. We'll make the dividend just a constant plus white noise, so that the fundamental solution is a constant plus white noise. What I'm going to do is see if we can learn the dynamics of the bubble process. So there's the bubble process, which we could rewrite as bt plus 1 equals beta inverse, that coefficient is slightly bigger than 1, times bt plus a arbitrary martingale difference sequence that corresponds to the arbitrariness of the bubble process. So that might be white noise or something more general. So you can invert that and put that back into the law of motion under rational expectations, and you get this. You get that pt is equal to constant plus beta inverse times pt minus 1, there's the explosive root, and then some terms involving the fundamental shock and the arbitrary martingale difference sequence. So now suppose we had agents as econometricians trying to learn how to forecast. So let's give them a perceived law of motion, pt equals a plus c pt minus 1, plus some terms on the other noise, exogenous noise terms, which we'll assume are observable for this. And notice that, okay, so the method to determine stability of a rational expectation solution under learning is you formulate a perceived law of motion for the agents. This nests both of the fundamental solution, which has c equal to 0, and the bubble solution, which has c equal to beta inverse, and the other parameters will fall in line. And then you can say, well, if they had that perceived law of motion where these parameters were fixed, actually they're going to be evolving over time because of the econometric learning. Suppose you had fixed parameters, whatever they are, a and arbitrary a, c, and so on. Then you could compute one step ahead forecasts. And I've done this on the assumption that exogenous variables at time t are observable, but not the current price. So you form expectations before the current price is realized. That does not affect the stability argument. It actually gives bubbles the best chance in this particular setting. So that's the forecast that they would then make. So you then insert that forecast into the model. By the model, I mean that thing. So insert that forecast into the model, and you solve for the actual law of motion that would be realized if agents had that expectation. That then gives you a map from perceived law of motion parameters to actual law of motion parameters. There's a fixed point at the fundamental solution where c is 0, that's the autoregressive parameter. There's another set of fixed points at the bubble solution where c is equal to beta inverse. And stability can be assessed by looking at this artificial differential equation. And inside that artificial differential equation is an autonomous equation in C, this parameter that at 0 is a fundamental solution and the beta inverse is the bubble. And then if you plot that particular differential equation, it's easy to see that the fundamentals value of 0 is locally stable under learning, and the bubbles one is not locally stable under learning. And so that led me to conclude that under least squares learning by agents, if they're econometricians, then one possibility is that you converge to the fundamental solution. If c goes to 0, then all the other coefficients fall into line. But if you start off in the wrong region, like a large value of c, then you'll tend to explode to infinity. So the prices may explode, but they're not going to go to a rational bubble solution. So you can think of this as an argument that rules out bubbles. You can also think of it as maybe it provides a source of bubbles if you can somehow tame this explosiveness. So I think that's been a theme in the bubbles literature that's recently reemerged under adaptive learning. Okay, so that was my concern about rational bubbles and why I became interested in near rational bubbles rather than rational bubbles, but we'll come back to that. So let me look at next some asset pricing where we bring in adaptive learning, but we are not trying to go for the big bubbles result, just more minimal deviations from the fundamental solution, but ones which may help us to match asset price dynamics. And I'll kind of build it up in stages. So I'm going to start off with the simplest change you can make using adaptive learning, which actually gets you somewhere. And that would be constant gain learning of the fundamental solution. So here's the setup there. And this idea goes back to Timmerman's papers in the early 1990s, where he basically argued that if you have adaptive learning in various ways you can set it up, there's going to be excess volatility along the path in which you learn rational expectations. So this argument basically just stretches that, those transitional dynamics to be persistent, permanent learning dynamics. So again, for simplicity, let's take the case where the dividend is just a constant plus white noise. There's our risk-neutral asset pricing equation, and all of this can be generalized to cases where you don't have risk neutrality, but it does substantially complicate things, and the spirit of this comes through nicely with risk neutrality. Okay, so there's the model. There's the fundamental solution. The fundamental solution is just a constant plus white noise. So under learning, we're just going to ask that our agents learn this constant. You can think of it as, yeah. So they're just learning the value of the fundamentals price, and the actual, under rational expectations, price would be a constant plus white noise. And so under least squares learning, let me do that first, pure least squares learning, they're just trying to learn this coefficient A. They'll have an estimate at time t. They run regressions on an intercept. Recursively, you can rewrite that as their estimate is last period's estimate plus 1 over the sample size times the most recent deviation of the price from the estimated intercept. Then they use that to forecast, that gives the price, and on we go. That's actually easy to show that will converge to the rational expectations fundamental solution. So our change is the constant gain change. So this T inverse is often called the gain. That's a decreasing gain. What if we replace that by a constant, some small constant number like 5% or 1% or 2% or whatever? So the motivation for this is usually given, is a plausible ad hoc motivation, which is maybe the agents think the structure might be changing. They shouldn't put as much weight on past data as on current data. Constant gain effectively is discounted least squares, where you weight recent data more heavily than old data. So we just geometrically discount old data. And you're led to this result. So now here's our recursive adaptive forecasting rule. Gamma is there, a small constant. So I've set up this model in a particularly simple way so that you can actually solve for the price process that results. So you get price process under constant gain learning. Price depends on lag price and the parameters, the shock, lag shock. That's an ARMA 1-1 process. You can compute its asymptotic variance. So it'll converge to you can check that it'll converge to a stationary stochastic process. You can compute its variance. You can figure out that, in fact, the variance will be higher than in the fundamental solution. And if you plug in, say, beta 0.99 and a gamma of 2%, it turns out the variance is twice as high as the rational expectations solution. So that was kind of a minimal deviation from, in the sense of, rather than having adaptive learning converge to the rational expectations solution, you have it converge to a stochastic process. It's around the rational expectations fundamental solution, but it does have different properties. It has excess volatility. You could redo this in other ways. If you had the price model as the expected, the infinite expected present value of dividends, you could get the same kind of result. Timmerman did it various ways like that. And I should mention that in other contexts, a simple exchange rate model with purchasing power parity has the same kind of structure. And one of the issues there has been the forward premium puzzle. And with former student, Chakraborty, we showed that if you did this sort of framework, and instead of having dividend white noise, you had it follow an AR1 process with a root near 1, then you could easily get the forward premium puzzle results. So I'll just mention that. Okay, here's another line of thought. So again, I think of this as a minimal deviation from rational expectations, but that you can get under adaptive learning. So another possibility is you underparameterize or you misspecify. In general, it's misspecify the forecasting models of the agents. One way you can misspecify is underparameterize dynamics. And so I thought the nicest example of this is by a paper by Fuster Hebert, I don't know how to pronounce his name, and Leibson, I don't know how he pronounces his name. And it was published recently in the NBER Macroeconomic Annual. So they said the econometrics evidence is not clear-cut, but you can argue that really the change in dividends is a high-order autoregressive process, like an AR30 process monthly. But what if agents don't fit that? What if they fit a lower order process? They think that the change in dividends is an AR1 or an AR5 or at most an AR10. Then it turns out that has implications. So they're going to be fitting a misspecified model for dividends. So they're using a model in which you forecast dividends and then the stock price follows from that. It's like for the fundamental solution, it would be the equivalent of writing down price as the discounted expected future dividends, and then the problem is how do you forecast dividends? They actually do this in a Cara preference model, Lucas type model. But anyway, what they argued was that if you fit an AR30 to dividends, then then dividends follow a mean reverting process. There will be a tendency for the long run persistence is less than 1. Whereas if you fit a low order AR process, you miss that. And so agents will tend to extrapolate dividend shocks where in fact they're mean reverting. But it would be natural for agents to fit a parsimonious model that misses that for 2 reasons. They give some psychological reasons, in other words, behavioral economic reasons, and then they give statistical reasons, which is that forecasters prefer parsimonious models for a variety of reasons. And so then they argue that you can fit a lot of the asset pricing anomalies in stock prices using that kind of model. From an adaptive learning point of view, they basically solve for a restricted perceptions equilibrium. That's the rational expectation, that's the misspecified analog of the rational expectations equilibrium. With adaptive learning, I would just add one other thing, which is that the agent should be estimating these parameters and updating over time. But anyway, okay, so that's another way you can get through the adaptive learning approach, or in that spirit anyway, you can get other kinds of asset price dynamics that are not there under rational expectations. Another approach to asset pricing that we'll see later today, I think, is due to Brock and Holmes. And I'm going to briefly say what they did and then briefly say how I've modified this in the past. So they use a setup that comes from the Cara normal approach. Under the Cara normal approach, you have agents that are trying to maximize the risk-adjusted present value of next period's wealth. So their agents have a choice between a riskless asset that pays guaranteed rate of return R, which is assumed constant over time, that's the gross rate of return. And alternatively, they can invest in a risky asset, that price PT, that pays price next period PT plus 1 plus a dividend next period YT plus 1. So they're assumed to buy now, sell next period. And that's their asset demand, ZJT, and that's the risk adjustment, which of course depends on how much of the risky asset they buy, and the conditional variance, sigma squared, and the A is their Cara risk parameter. So in general, the Brock-and-Holmes approach was you've got this dynamic predictor selection approach, which I'll quickly describe, is you've got different forecasting rules, and different agents use different forecasting rules. Maybe there are J classes of agents. Given their forecast, they solve this problem. That gives their asset demands, ZJT, which depend on the expected excess returns and also inversely proportional to the conditional variance. In the paper I'm mentioning from the JEDC in 1998, they take sigma squared, that conditional variance is constant, which it would be in a rational expectations equilibrium, but I'll come back to that. So there's different classes of agents have different demands because they have different forecasts of the expected rate of return. Let's take the simplest case where there are just two classes of agents. So this is a heterogeneous expectations model. And then the equilibrium is that the random asset supply is equal to demand, and N is a proportion of agents using forecasting model 1, and Z2T is, 1 minus N is the proportion of agents that use the other model. So when you combine all that, that's a temporary equilibrium, what I call the temporary equilibrium price. It's driven by the forecasts and by the dividend shocks and the supply shocks. Rho, I guess, the dividend is assumed to be serially correlated with a coefficient that's known. So the spirit of the Brock-and-Holmes approach is you have a variety of rules of thumb, agents that are plausible. Agents have those on the table, and then the proportion of agents that uses one rather than the other depends on recent forecast, recent fitness, I guess you call it, on the forecast performance, but measured in terms of utility or profits in this case. And this could be profits for that rule or risk-adjusted profits. And then the fitness is measured by the most recent value, plus you can fold in past values. So there's a parameter there that you can set, eta. And then the proportion of agents using one rather than the other forecasting rule depends on the relative fitness through this logit formula. There's a parameter there that controls things called the intensity of choice psi. If psi is very high, then almost all of the agents use the best fitting model. If psi is low, then they're more balanced. Okay, but it's dynamic predictor selection. Every period, every period you look at the forecasting performance last period, that gives you a proportion, and then it evolves. And what they show is you can get a lot of complex price dynamics with appropriate settings of parameters, and there's some bubble-like behavior that can certainly arise in this setup. They have a big focus on the nonlinear dynamics that can arise. So that's what they do, and here's a variation of that theme, which Bill Branch and I worked out, which is let's do the same thing, but let's have least squares learning too. And so rather than rules of thumb, I like my agents to be more like econometricians, and so I want them to actually fit models and estimate them as well as assess their performance. So what's the simplest thing we can think of there? Well, there were two driving processes here. Let's make them each AR1. There's a dividend process and a risky asset supply process. Let's assume they're exogenous, that they're AR1 processes. And there are two kinds of agents, those that think that really prices are driven by dividends, and other agents, the other model is that prices are largely driven by asset supplies. And so each of those can be estimated. They can estimate a model which they can then use for forecasting, since they know the serial correlation of those two exogenous processes. There are other ways you could set it up that are almost equivalent. And then we'll just watch what happens. So, the spirit in this model, the natural reaction would be, okay, so why don't they use both variables? So the spirit of this is the world is really very complicated, and you can't include all of the variables. If you think about VAR models for the macroeconomy, you run out of degrees of freedom very quickly. It's a big problem. Similar thing would happen for forecasting stock prices, as we know. So we're just going to assume that just as forecasters recommend parsimonious models, they've shown for practical forecasting, parsimony beats having a specification that includes the truth. So let's see what happens in this little laboratory where they just use one of the two variables. So what we show in the paper is that there can be multiple, in this particular setup, with the fact, because of the fact that expectations feed back with a strong positive coefficient into prices, there can be two misspecification equilibria, as we call it. And so I'll just give you the essence of the argument there, which is, so n here is the proportion of agents that use model 1. So n equals 1 means that almost all the agents are using n equals 1. And f of n is the relative profits, risk-adjusted profits that they make compared to the other model. So if almost all agents want to use model 1, then you'll want to use model 1 too. If almost all agents want to use model 0, then you will want to use model 0 as well. There's another equilibrium in between in which you want to split between model 1 and model 2, but that one's not stable under learning. The n equals 0 and n equals 1 are stable under learning. If you have a finite intensity choice psi, that moves you away from n equals 0 and n equals 1, but it's still close. And those two misspecification equilibria are different, though. They have different volatilities, for example. It's not. So again, I'm not going to show you the details of this one, but now just make one other step, which is you add constant gain learning to the forecasting rules, and you also have that an equivalent constant gain for assessing the forecasting performance. And then it turns out that you get a model in which asset prices exhibit parameter drift and regime switching. Both, there was a stage where Sims was arguing for regime switching and Sargent was arguing for parameter drift, so we get both of these in this model. You'll be sitting there in one of the equilibria, most of the agents using one of the models, and then a series of stochastic shocks will make the other model, the other forecasting model, look better. And so then they'll all switch to that one. But meanwhile, within each model, the parameters are drifting around a little bit because of constant gain learning. But what you will see with regime switching is you'll be in a high return, high risk regime, high volatility regime, and then you'll switch, and then for a period of time, you'll be in a low return, low risk as measured by the conditional variance regime. So there's a kind of a self-fulfilling prophecy going on there. Okay, now let's go back to the bubbles side of things. Let me try and make bubbles more workable. So my problem there, as I mentioned at the beginning, was that bubbles appear to be unstable under adaptive learning, these explosive bubbles, the ones that grow at rate 1 plus r in expectation. There are going to be various ways to tame it. Our intuition comes off of this quote from Alan Greenspan. It's one of the quotes we like from him. And I'll just pause while you read it quickly. It basically says risk is important. Estimates of risk vary over time, and estimates of risk are important for the stock market. Good enough. Okay, so bubbles seem to be, rational bubbles are unstable under adaptive learning. If you want a theory of bubbles that has adaptive learning, you've got to tame the bubbles somehow. You need a mechanism to prevent prices from exploding to infinity or to 0 for that matter. And I think there are three natural possibilities. One is you impose a projected facility. You basically have a device that ensures that prices just don't explode too much. I think that's one very natural way to do it, and a nice example of how to do it is in a paper by Adam Marcet and Nicolini, and I don't know if that's what Albert's going to talk about. I'm sure he'll talk about something related, so you'll hear more of that. Another way to tame bubbles, which is used by Carsames and his colleagues, is just make sure that as you set things up, there are enough fundamental forecasters in the model. Okay, so you have to make sure that there's just enough of those so that prices get way out of whack. They really drive prices back to the fundamentals. So that's also a very natural way to do things. And then this way is based on the fact that agents may estimate a risk in real time, and their estimates of risk may go up at times of bubbles to pop the bubbles. At times, estimates of risk may also be very low, and that may lead to bubbles. That's the risk. That's part of the Greenspan comment. There is that there are these periods when there are lower risk premiums than normal, and that leads to price increases, and eventually people realize that prices are more risky than they thought when prices collapse. Okay, so this is now we're just going to have one forecasting model again. I'm going to emphasize something different, so get rid of the heterogeneity. We're all going to use the same forecasting model. This is in the same kind of one step ahead Cara normal framework. Okay, and so the asset demand for the demand for the risky asset depends on expected returns minus the returns if you invested in the riskless asset. So this is the expected excess returns of investing in the risky rather than the riskless asset. There's our risk aversion parameter A, and sigma t squared is now our estimate of the conditional variance. So we have to estimate returns, we have to forecast stock prices, and we have to have an estimate of their conditional variance. And then we face demand and supply, and that gives us this simple equation for the temporary equilibrium of stock prices, but now it depends on expected returns and expected risk. So we're going to keep things really simple in this sense. We'll make asset supply white noise, and dividends are just a constant plus white noise. I guess asset supply was a constant plus white noise. They're both constant plus white noise. So under rational expectations, it's again, there's going to be a constant risk, constant sigma squared, and prices are going to be a constant plus white noise. So there's the fundamental solution. Again, there's a bubble solution with constant risk. That's easy to write down. That's the one that's unstable under learning that always makes me unhappy. And Xi here is an arbitrary Martingale difference sequence. That would be the rational bubble. Okay, and so we've still got those in the background. The paper now says, well, what if agents had a perceived law of motion that nested those solutions? So we're going to allow price to depend on expected price. In the fundamental solution, price is just a constant plus white noise. We'll allow people to forecast assuming that price depends on lagged price. And so you can look for, just if you posit that as a perceived law of motion, you can go through the learning exercise that I did before. I won't go do it again. You discover that the fundamentals, rational expectations, equilibrium is locally stable under learning. Discover that the bubbles solution is not stable under adaptive learning. Okay, but now the additional thing that we have discovered is that under constant gain learning, so they have a constant gain on the parameters that they're learning for the price process. They also have a constant gain on their estimate of risk, which is just a simple recursive estimate of risk based on the squared excess rate of return. And what we find is that, yes, if the gain is small enough, then you are close to the rational expectations fundamental solution. But if you increase the gain, particularly on the risk estimates, to not particularly large levels, but levels like 0.04, that you'll be in the fundamentals equilibrium for a period of time, and then the parameters will escape to a new region. And it's not the bubble solution, but it's close to the bubble solution. You escape to a random walk region. So remember, in the fundamental solution, price is a constant plus white noise. There's no dependence on lag price. But there will, with certain sequences of stochastic shock for supply and dividend, will push the risk estimates, push the parameter estimates to be a random walk, constant of 0 and a AR coefficient of 1. And in that regime, risk estimates have a huge role. They really move prices around a lot. And so you get then a period of recurring bubbles and crashes, and you can think of this as escape path dynamics. So here's some stochastic simulations. I'm just going to show you what happens in this model as you increase the coefficient, the gain on the estimates of risk from 0.1% to 4% per period. And so that if it's low enough, that's basically very close to the rational expectations fundamental solution. It's very noisy, obviously. But anyway, you can see the coefficient, the autoregressive coefficient in the middle panel is near 0. The risk estimates are wandering around the rational expectations equilibrium value. The price is the constant plus white noise. That's the actual price. And then you turn up the risk estimate parameter, and you can begin to see some movements. You see a few journeys here into the random walk regime. And you can also see that there are occasional spikes in risk estimate, and you can see there are crashes and bubbles. And then if you jack up the parameter a bit more, you just spend more time in the random walk regime where changes in risk are driving the volatility of prices, the bubbles and crashes. So there's these, again, periods where things are quiet and then periods where there's a lot of action. One comment we got on the paper was, what if agents had a more sophisticated estimate of risk rather than just think of it as a constant gain estimate of a constant, which happens to vary over time because of the gain? What if they fit an arch model? And what we found was that if they fit an arch model, that just made things even more, the role of risk was even greater. It could have gone either way. It reinforced our results. So I guess I've got one other model to go through. I've got 5 minutes. Okay, I think I can just about do that. Yeah, this is related enough that I wanted to get this in. This is, this is on the, so as I'm concluding, the main point I want to make here, apart from the variety of things you can get from adaptive learning in these simple models, is the importance of the feedback parameter, beta there. Call it feedback, you could call it feed forward. Anyways, the sensitivity of current prices to expected prices in the following period. Beta here is a parameter that comes from the discount factor, and so it's close to 1. So there's a lot of feedback of expectations. Notice that if beta were literally equal to 1 and UT were 0, then anything would be self-fulfilling. And if beta is bigger than 1, you'd have multiple well-behaved rational expectations equilibrium. So it's not too surprising that if beta gets close to 1, a lot of interesting things can happen. Okay, here's one other variation on the theme. This is a paper with Seppo Honkapohja and Jim Bullard. Suppose we have the same setup we had before with, I guess this is the one step ahead Cara normal framework. Here I've deviated everything from the fundamental solution. So YT here, Y is not dividends, Y is price. And UT is a supply shock. And the dividends were there, but they've been substituted out through the fundamentals price. Okay, so YT, the deviation of the price from fundamentals price, depends on the expectation of that deviation plus a supply shock. And again, we're fixing the conditional variance as constant. Okay, the wrinkle here is, suppose we have econometricians that estimate the model, but people don't just use the econometric forecast, they add judgment. Okay, so Jim Bullard was interested in this because he noticed the role of judgment in monetary policy. They had their econometricians, they made forecasts, and then the experts get together and they say, no, the models are leaving this and that, we'd better add this judgment about what happens. And we became interested in, well, what if you add judgment and it's some exogenous serially correlated process, XIT there, but that judgment actually is extraneous. So it's unfortunately, it's not good judgment, it's random judgment. It comes with a story always, but anyway. So we look at, could there be something we call an exuberance equilibrium? In the exuberance equilibrium, we have 3 properties. One is that the time series dynamics for the econometric section gets it right. Okay, I set up everything with white noise, but judgment serially correlated. It turns out that if every agents are using that and making the judgmental adjustment, then the time series process of the actual price process will be an ARMA 1-1. And so they have the right coefficients. The econometricians get the coefficients right. They fit the right ARMA 1-1 process. Secondly, there are incentives to use the judgment. If you're in a exuberance equilibrium, in other words, one that actually includes a judgment, then you want to include the judgment rather than just use a straight econometric forecast. And the third thing is learnability. We want the econometric learning rule to actually be stable. So regardless of what parameters you start off with, you converge to it. So it's stable under adaptive learning. In this case, it has to be recursive maximum likelihood learning. And then the result is, yeah, beta is bigger than a half. In other words, if there's enough positive feedback, beta is less than 1. But if it's bigger than a half, then you can invent judgment processes with the right serial correlation parameters that will meet all those conditions. They will have excess volatility. And in fact, it's easy to fit them so that they have a factor of 10, let's say. So the conclusion was waves of a judgment to adjust for perceived omitting fundamentals might become self-fulfilling if the feedback is high. Okay, let me take -1 minutes to do the conclusion. So strong positive feedback, that's going to open the door for a lot of new price dynamics. And there are a lot of simple ways to get quite a lot of mileage, and then there are some more dramatic things like dynamic predictor selection that can lead to regime switching, and ways you can get near rational bubbles. And just let me conclude with these 2 points. One is an open question from my point of view is the role of heterogeneity. So I've had models with heterogeneity and had models with homogeneity. Obviously, there's heterogeneity in the data. We see there's heterogeneity in expectations as well as other features of agents. What's not obvious to me is whether to get exciting price dynamics, realistic price dynamics, you have to have that heterogeneity in the model or not. I just can't decide. Mondays, Wednesdays, and Fridays, I think it's important. Tuesdays, Thursdays, Saturdays, and Sundays, I think, it's self-fulfilling delusion that matters. And that can be homogeneous. But anyway, that's an open question. And then the last thing is, on the cognitive consistency principle, I stressed agents that are as smart as us, not smarter, but as smart. The reason I'd like to make them as smart as us is simply that whether we make them theorists or econometricians, is I think that defines the limits of what's possible in terms of coordination, which is the theme of the conference. So, if they're not as smart as us, then it's not so interesting. If you assume they're as smart as we are, and you get all these kind of interesting dynamics, then that surely says something about the economy. Okay, sorry.
Okay, thank you very much.